Okay, so hello everyone. I'm Andrei, and together with my colleague Catalin, we worked on a few optimizations for the CDSAPI data retrieval, which we want to show you today. So first, let's see why these optimizations are needed. So first, we would like to avoid requests that have as a response datasets that contain empty data, because those are just a burden on the system and are actually not useful, as they can be efficiently rebuilt locally by reuniting the composed request. To imagine this in a better way, we can think of it geometrically. A data set can be seen as a hypercube. Of course, it may contain empty spots because there are certain fields for which there are no measurements or that don't really make sense together. Also, for each of such hypercubes, there are subcubes, which are called constraints, and their properties that they don't contain empty spots. So yeah, we would like to make requests that don't contain empty spots and locally rebuild them such that we don't overload the system. And the second optimization that we worked on is regarding avoiding expensive requests. So of course, a very large request can be heavy on the systems. Users get penalized when they make such requests, as there are guidelines stating that these things should not be made. But the solution would be to make multiple smaller requests. This reduces the workload and ensures that users stick to the guidelines. Okay, so on the previous slide, I talked about constraints. This is how a constraints files looks like. So what does this mean? If you look at the source, you can see that there is soil, and for version, if we choose, for instance, version latest and variable nitrogen oxides, this is present in the constraint. So this means that we have data for this variable, so there is no empty spots. But if we were to choose, for instance, soil as source version 3.1 and variable nitrogen oxides, since this is not present in the constraints, there is no data available, so an empty spot appears. Now, in order to represent these constraints and work with them, we decided to use a dictionary of sets as a data structure. This is basically an unordered map or hash map, whatever you want to call it, which contains as these strings, so the name of the variable, and as values sets containing all the possible values. Now, let's talk about the first optimization more in detail. So how do we split a request to make sure that it doesn't contain any empty spots? Our first idea was to intersect the request with each and every constraint. Of course, since constraints have the property that they don't contain any empty spots, this would guarantee that the resulting set of sub-requests does not contain any empty spots. The problem with this is that the number of sub-requests is not minimal, and it can be actually very large for large constraint files. So then the second step was to reduce the number of sub-requests that result from this operation. We noticed that sub-requests can be reunited without creating empty spots if they differ by only one variable. And of course, this is very important. Order of merges matters. So if we decide to merge two sub-requests before another two, this might result in a different minimal set of sub-requests, and it will have an effect on the solution further on. Let's take a look at an example. So let's say that our initial request, we have the same constraints file that you previously saw. We have an initial request for source aviation and soil, version latest and 1.1, and variables nitrogen oxides and acetylene. After intersecting with each line in the constraints file, we get the following three sub-requests. And notice that the last two sub-requests can be merged together because they differ only in the version field. So after the reunion, we get those two sub-requests. This is the minimum number. We cannot merge this anymore because we would get empty spots. And after the reunion, if you look at the constraints file with this sub-request, there are no empty spots. Okay, now making this reunion is not that trivial, mostly because, as I said previously, the order of the merges matters. So one of our first ideas was to use a backtracking strategy, which just tries to generate all or most reunions between sub-requests. One of the backtracking strategies relied on generating all the permutations and then reuniting them. But this, of course, is extremely slow. Then we tried another approach, which relied on generating connected components. So trying to draw an edge between two sub-requests, and that edge meant a union in them. This is faster because we can rule out some cases, but it doesn't try all the options. But still, it tries quite a lot of them. And of course, because of that, is still quite slow. Then we thought about some heuristics, and we came up with the maximal and minimal dimension reunion. Basically, we select the dimension after which the union is done, and it's either the one that yields the maximum size or the minimum size after the union. This, of course, is very fast because it doesn't try that many options. It just goes in the way that the algorithm has to. And because of that, it doesn't guarantee a minimum number of sub-requests. It's an heuristic after all. Yeah, and in order to figure out how good or bad these strategies are, we did some experiments. You can see in this table the results that we got. So overall, the best strategy was the heuristic with the maximal dimension strategy. You can see that it reduces quite a lot the size after the reunion, and also it is very fast compared to the others. The backtracking strategy, as expected, it's slow. This is the connected components one. And because it's the connected component one, of course, it doesn't yield necessarily the minimum result. So that's why in some cases the maximal dimension strategy returned a smaller result. And yeah, the minimal dimension strategy turned out to be quite bad. It's fast, but the number of requests doesn't get that small.
As previously mentioned, the user need to follow some guidelines in order to make the request small enough in order to not burden the server and get penalized for the big request. To fix the problem of large requests, we need to split the initial request in smaller sub-requests. And we do that by choosing a dimension after which the splitting is done. And we came up with 5 approaches to choose that dimension: splitting by the dimension with maximal size, splitting by the dimension with minimal size, splitting on a dimension order, splitting on a random dimension, and splitting on the dimension with maximal cost reduction. The new size of the dimension is calculated based on the current dimension size, the overall request cost, and the maximal request cost. The last two parameters are retrieved by default from CDS API, but in case custom costing function is needed or a custom maximal request cost value is needed, they can be passed to the request optimizer. Now the cost of a request is calculated by multiplying the sizes of all the dimension in the request. But we've came up with multiple approaches in case something to keep the solution flexible and in case something changes in the future in how the cost is calculated, um, to be able to do the splitting in a performant way. Let's say, for example, in the future, maybe the cost will be calculated based on weights. The splitting on a dimension order would be the most suitable strategy. Here we have an example of a mock request with the cost 60 and the max cost 30. And the strategy chosen is dimension with maximal strategy. So we split by the year dimension. And as you can see, it will result in three sub requests. Also, here we have the same request, but in this case we have max cost 11. As we can see, the first split is not enough. So the solution will split each sub request from the first level again, this time by the day dimension. Our solution, the new CDS API client, is a wrapper over the current client, which performs some extra steps before making the requests. First, intersects the request with the constraints, unifies them to be sure that we have a more minimal number of sub-requests, and optimizes the expensive requests. And only after that, the requests are made in a traditional way using the current CDS API client. Also, our solution accepts some extra parameters, like the directory where the data to be saved, if the sub request should be executed in parallel or not. The user also can select the strategies for both request unification and request splitting. And finally, the solution will output a log file containing all the sub requests, the corresponding file, and the cost of the sub request. In conclusion, we've implemented multiple strategies for both reunion and request splitting, and we've concluded that the maximal dimension strategy is the most effective, is the fastest, and is very effective for the reunion. The backtracking strategy being more accurate in theory, but is very slow. And for the request splitting, from our tests, the dimension with the maximal size was the best. And as for future work, a better logging system could be implemented, and also an integration with the solution from the other team would be a big plus. Now let's see it a bit in action. Here we have a request for CAMS Global Atmospheric Composition Forecast dataset from ADS. And the request contains variables, 8 variables, single and multi-level variables. Let's execute it in parallel. As we can see from the log file, we have two sub-requests. The first is for the multi-level variables, and the second one is for the single-level variables. And we have the corresponding files for each of the requests, sub-requests, and the cost. We can see the costs are 32 and 40. And after Everything is done. We can make another request, setting the max cost to 30 just for demonstration purposes. As we can see now, we have 4 sub requests, each one of them having the cost below 30. Thank you for your attention. Questions if you have.